Hi everyone, in this session we're going to be having a look at elimination reactions with the haloalkanes. And we have got four objectives. The first of these objectives is to be having a look to see if we can define the term base, which hopefully is something that is familiar to you from previous sessions. Secondly, we are going to be recalling conditions and reagents for the elimination reactions of haloalkanes. You're going to be able to draw the mechanism and also explain the formation of isomers in these reactions. Firstly, let's consider why we're thinking about being able to define the term base. What we have is our hydroxide ion here. Remember that negative charge is actually on the oxygen. And if you think back to last session, we looked at this hydroxide ion as a nucleophile. And we said that a nucleophile is an electron pair donor. That's what we had last time for our OH minus, that hydroxide ion. So that's behaving as a nucleophile. However, OH minus we are very familiar with as a base, and a base is actually a proton acceptor. So that is what we're going to be looking for in today's mechanism. We're going to be looking for the situation where our hydroxide ion, our OH minus, is going to be acting as a proton acceptor and therefore as a base rather than as a nucleophile. Whether my hydroxide ions are going to be acting as a base or as a nucleophile all comes down to the conditions. So it's very important that we get these right. So we would have, say, potassium hydroxide here as the source of my hydroxide ions, and it would be in ethanol. There's no water present. Okay? Another way to write that is that it's an ethanolic solution. So again, it means no water present. It means the potassium hydroxide has been dissolved in ethanol. And then also we would have the haloalkane in ethanol as well. So no water present, and this means that my hydroxide ions are going to act as a base. Let's look at the elimination reaction here with our haloalkane. So elimination, that is telling me that a small molecule is removed. So we're going to consider what that might be as we see the rest of the mechanism. And we're going to start by considering this OH minus acting as a base, so therefore a proton acceptor. And we have got haloalkane. So our haloalkane, let's just consider a simple haloalkane here. We're going to use X to represent our halogen as usual. Pop that on there. And then we're going to have our OH minus. I'm getting all the colours going here. Let's have the OH minus here. And I've written it this way round just to make it a bit more straightforward, to have that arrow heading there towards that proton. Remember that hydrogen there, it's going to come off as H+, it's a proton. Both electrons that were in that bond, one of which did belong to the hydrogen, now have been stolen away, heading in towards here to that bond between the two carbons. And then we've got our X acting as our leaving group. So we've got three arrows that we need to draw in this elimination reaction. And we can see then the product that we will form in this case. So start by drawing all the bonds that still remain, so the things that didn't change at all. This is how you're going to keep track of things. And then we draw what's different. So we now have a double bond here. Where that arrow across here went in, it was both electrons from this bond now going into here, forming a new bond between the two carbons. So it goes with the one that was already there. So that's now a double bond. And what do we have left over? Well, my hydroxide is now attached to hydrogen which it accepted, that proton that it accepted from the original haloalkane, and I also have the X minus there, which is my leaving group, so chloride, iodide, and so on. So hopefully we spot it there, that is H2O, and that has been formed because the OH minus here picked up that hydrogen. So it's common sometimes to make the error in thinking that you're going to end up with the H and the X together because they're the two things that have left your molecule. But remember that the reason this hydrogen left the molecule is because it's been picked up by the hydroxide ion. That is keeping hold of it in the water. And so now we have this X minus, whatever that may be, just present in the solution. We can write an overall equation for this reaction. So we can start off with the hydroxide. We can't get hydroxide ions on their own, of course, in our experiment here. So we would have, say, potassium hydroxide or sodium hydroxide. Then we have got our haloalkane, whatever that may be. Then we have formed the alkene. So we could just represent this like so. There we are. And also then the water. And if we'd started with potassium hydroxide, we'd then write this as Kx at the end. So we'd have potassium chloride or whatever would be relevant to the particular halogen that we had. Let's look at a specific example so we can consider why we might form isomers in our elimination product mixture. Here we have 2-chloropentane, and we can have two different attacks here by the hydroxide ion on our 2-chloropentane. So one option that we can have is that the hydroxide ion acting as the base is going to attack the hydrogen on carbon number 1. Remember, the chlorine is on carbon number 2. So if we just do the same here on this one, 1, 2, 3. And on this side, the hydroxide ion could attack a hydrogen that's on carbon number 3. So either way, remember that the hydroxide ion has to be picking up a hydrogen that is on a carbon which is adjacent to where your halogen is. So if my halogen here is on carbon number 2, my hydroxide ion has to collect a hydrogen from carbon 1 or 3. Sometimes this isn't going to give us isomers because sometimes we're going to have symmetry such that it won't make any difference. But in this case, where we have got 2-chloropentane, we are going to get isomers. So let's look at what the next steps are within the mechanism. Put the rest of our curly arrows on. So you could pause your video here actually and do two for yourself. Come up with the two products and name those products. Well, what happens is this bond here is going to go into there. That's where I'm going to form my double bond. And this bond here, those electrons in that bond go onto the chlorine. On this side, it's this bond going into there. And the chlorine, it's my leaving group, still happens like that. So what do I have in terms of products? Well, let's focus on these organic products. So I've now got a carbon-carbon double bond there between carbon 1 and 2. You can see that's where those electrons have gone. That's where that double bond is going to be. And then I can draw in the rest of my molecule. So I've got the two hydrogens that are still on there. Then hydrogen here. And then here I would have a CH2, that's carbon number 3. CH2, CH3. You might have drawn this out as a fully displayed formula, but alternatively you can draw it this way. This way I prefer because it's going to be a bit easier for us to start thinking about the isomers that we may have. And then on this side, I've got the carbon-carbon double bond between carbons 2 and 3. So therefore I've got carbon number 1 here as a methyl group. I've still got a hydrogen there on carbon 2, that didn't go anywhere. And then still a hydrogen here, and therefore put the rest of this on, so that's going to be carbon number 4 there, and this is carbon 5. So what we have now is pent 1-ene and pent 2-ene, and we can also see that pent 2-ene could exist as 2 stereoisomers. So this version that we've drawn here, we have got our largest groups, our highest priority groups on the same side, so that if you remember way back to when you did isomers, Z and E isomers, that is your Z pent 2-ene. You could just as likely drawn it the other way around, so you'd still be correct if you had drawn the E pent 2-ene. It's actually both of those within our mixture alongside the pent 1-ene. Now let's review what we've seen in this session. So hopefully now you feel that you can define the term base. You can recall, or hopefully with some practice, you'll be able to recall the conditions and reagents for the elimination reaction, remembering that it's that sodium hydroxide or potassium hydroxide in ethanolic solution. You can draw the mechanisms. Remember, we're looking for 3 arrows. They're going to follow each other, and they start on the lone pair of the hydroxide ion. Arrows always starting at a lone pair or at a bond. And finally, you can explain the formation of isomers in the elimination reaction product mixture. So it all depends upon which hydrogen is initially removed by our hydroxide ion, which is acting as the base. So if you can do all that, that is fantastic. Give us our smiley face. Well done.